coils we have. This is
Yeah.
one coil, this is another coil. Two coils we have, and this I am removing this now. There is no current. Initially, there is no current in any of the coil. Initially, there is no current in any of the coil. So here also there is no current. This is coil number one. This is coil number two.
Yes,
Now,
sir.
this coil is basically a solenoid. This coil is basically a solenoid, and we have seen that whenever there is a current, whenever there is a current in solenoid, whenever there is a current in solenoid, there is a magnetic field in the
Yes,
solenoid.
sir. Yes,
Which
sir.
basically solenoid is an electromagnet. Solenoid is an electromagnet, so there will be an there will be a magnetic field in the solenoid. Okay, basically. So this is a coil. This coil number one is connected with a battery, and here is one key. Here is one key, and this time this key is open. This time this key is opened. So now I am just closing this key. Now this key is closed, so this is connected with battery. So there will be the some current. There will be some
Some
current here,
current. Yes, sir.
current in the circuit. And in this circuit, when you just close the switch, the current will start increasing in this coil. The
Yes, sir.
current will start increasing, means the magnetic field in this coil will start increasing, and the effect of that magnetic field due to the coil will be here also.
Yes, sir.
Magnetic field due to this coil will be here also. So as the magnetic field, as the current is increasing, you can say here also the magnetic field is increasing, and magnetic field is directly proportional to the magnetic flux, because magnetic flux
Yes.
is given by B dot A. So basically, area of the coil is constant. If we are taking the area of the coil as constant, so your magnetic flux is directly proportional to magnetic field. So if the magnetic field of this coil is increasing, then we can say the magnetic flux of this coil is increasing. And we know that according to the Faraday's law of electromagnetic induction, when there is a change in the
Yes,
magnetic
yeah,
flux,
yeah.
there will be an induced EMF.
Induced EMF
So
yes.
there will be an induced EMF in this coil, and due to that induced EMF, there will be an induced current. So this there will be some deflection in the galvanometer. There will be some deflection in the galvanometer,
Yes, sir.
and there will be some induced current. There will be some induced current in the coil too. Basically, this is the phenomena happening, and this phenomena is known as the mutual induction. Means whenever you are changing the current in one coil, there
It
will
will
be
happen in
some,
same
yeah,
coil too.
there will be some current induced in another coil. This is
Yes,
the
sir.
phenomena of mutual induction, and this will we will study in the transformer, because transformer is based on the principle of mutual induction.
Yes, sir.
So this is the explanation. Okay, V1 is the magnetic field produced in this coil number one. So when this magnetic field is increased, so flux will increase here. Okay,
Yes,
so
sir.
basically you can write this, you can remove this, you can write this. V1 is the magnetic field in coil 1. V1 is the magnetic field in coil 1.
Yes.
This is the magnetic field in coil 1. Why there is a magnetic field in coil 1? Because there is a current in coil 1.
Current pass through. Yes, sir.
And why the magnetic field is increasing? Because when you just closes the switch, current is start increasing from 0 to some value. That is why the magnetic field is increasing. And if the magnetic field is increasing in coil 1, this magnetic field will be here also. Magnetic field lines due to this coil will be
Yes.
here also. So as the magnetic field is increasing,
Yes,
so
sir.
magnetic flux in the second coil will also increase. Okay, so phi 2 is the magnetic flux in coil 2. Phi 2 is the magnetic flux in coil 2. So basically you can say this magnetic field is directly proportional to the current. This magnetic field is directly proportional to the current. If you will increase the current, then magnetic field will increase. So basically you can say this flux in the coil 2 is directly proportional to the current in coil 1. Okay, if you will increase the current in coil 1, there will be increase in the magnetic flux in coil 2. So when we will remove this proportionality sign, we will get a coefficient of mutual induction. we will get a coefficient of mutual induction.
Mutual
we will get.
induction.
Yeah, this is phi 2. Phi 2 is the magnetic flux in coil 2. M is the coefficient of mutual induction. I1 is the current in the coil 1. I1 is current in the coil 1. Okay.
Yes, sir.
So basically, this is the definition, or you can say expression.
Yes, sir.
Whenever current in coil 1 change, EMF is induced in the
Induced in the
neighboring
coil.
Neighboring coil.
Yes, sir.
So you can see here, current is changing in this coil. This current is increasing. Induced current will be there in the another coil, neighboring coil. This is the neighboring coil. Okay. So due to the change in the current in the coil 1, what is happening?
Coil
Flux
2
linked with the coil 2 is changed. And
EMF
due to that,
induced in
EMF induced in the coil 2 and hence induced current in coil 2.
Coil
This
2.
is the phenomena, and this phenomena is known as the mutual induction. Mutual induction. This phenomena is known as the mutual induction. So now there is one coefficient of mutual induction here. This is the coefficient of mutual induction. So coefficient of mutual induction is constant, but this depends on certain factors.
Yes, sir.
Separation between the coil. Separation will be between the coil
Distance
depends upon the
orientation.
Orientation means how the coil is placed. What are the orientation of the coil? Geometry
Yes,
of the
sir.
coil. What is the geometry of the coil? The length of the coil is large. The diameter of the coil is large, like this.
Yes,
Nature
sir.
of the material of the coil. So basically,
Yes.
this is the this we get experimentally. Okay, this we get experimentally. So here, this is very easy thing. This is very easy thing. We can say uh, here, flux is directly proportional to the current. I have told you, when you will change the current in coil 1, there will be change in the flux in coil 2. So you
Yes,
can say
sir.
magnetic flux is directly proportional to the current. When you will remove this proportionality sign, you will get this M. And we know that induced EMF is given by minus d phi by dt, Faraday's law.
Yes, sir.
Faraday law.
Yes.
Faraday's law. Okay. Now d phi by dt. Phi is mi. Phi is mi. When we will put this phi here, we will get minus d by dt of mi, and this coefficient of mutual induction is constant.
You have
So
to come
we
out
can say
M minus M di by dt.
yeah, we can say the EMF induced. This, what is E? E is the induced EMF in coil 2. Induced EMF in coil 2 is given by minus M di by dt. What is E? E is the induced EMF.
Induced EMF.
Induced EMF in coil number 2. Induced EMF in coil number. So from this formula, we can calculate the unit of this coefficient of mutual induction. Okay. So coefficient of mutual induction, when we will rearrange this will become E into dt divided by di. So unit of E, small e is volt, unit of dt is second, unit of SI unit of current is ampere. So volt second per ampere is known as the Henry. Henry. Okay. So this is known as the Henry. So if you want to define 1 Henry, then this is also very simple. So what you will do, you will write this formula and you will take this value as 1 and you will take this value as 1. Means you will take di by dt as 1. This is here, see here. For 1 Henry, if you want to define 1 Henry, like you have defined 1 coulomb. 1 coulomb. So we will define 1 Henry. For 1 Henry, take mod of E is equal to 1. Magnitude of induced EMF is equal to 1, and change in the current with respect to time, take 1 and put in this formula. This is M, na?
Yes, sir.
So this formula will be E di by dt. You will get 1 by 1 is equal to 1 Henry. So basically, what is your 1 Henry? 1 Henry is the rate of change of current of
1 ampere per second.
If rate of change of current of 1 ampere induced an EMF of 1 volt, then mutual induction is equal to 1 Henry. Then the mutual induction of the coil is 1 Henry. Okay. So mutual induction is very simple phenomena. This is based on the electromagnetic induction. Okay. This can be explained with the help of Faraday's law. Okay. So note down.
Yes, sir. So can you scroll up? Sir, I think the page changed.
Write the heading mutual induction. Mutual induction.
So you can scroll down.
Scroll down. Okay.
So you can scroll down.
Yeah. Harsh, have you got it now? What is mutual induction?
Yes, sir. Yes, yeah.
When there is a change in current in one coil, there is an induced current in another coil. And why,
Yes,
if someone asking why there is an induced current in another coil? Because see here, just wait a minute, See
Yes,
here,
sir.
there is no physical connection. You are changing
Yeah.
current in this coil. You are changing current in this coil, and there is no physical connection between this coil and this coil. If you are changing current here, then there is a deflection here.
Yes,
Why
sir.
this is happening? This phenomena is happening because there is a change in the magnetic flux linked with the coil 2 when you are changing the current in coil number 1, and change in the magnetic flux produces or induces EMF in coil 2, and due to that there will be an induced current. Okay. Down.
So can I scroll down?
Have your examination completed? All of the examination?
No, sir. One exam is left.
Which subject?
Computer.
You have a computer?
Yes, sir.
Which language?
Sir, Python.
Very good.
Sir, but it's not easy, sir.
Python is, I think, the easiest language of them
Yeah,
all.
it's easy in terms of like the languages, but it's not like programming confusing, sir.
Yeah, I know, but if you will compare Python with JavaScript with
Yeah,
C++,
it's much easier.
then it is much easier. And in data science today, today's world, Python is they are using Python.
Yeah. So can you scroll down?
Yeah. So 1 Henry, if you want to define, so you will use this formula and you will use change in current with respect to time is equal to 1 and induced
Yes.
EMF equal to 1. You will get the coefficient of mutual induction is equal to 1.
Yes, sir.
So Henry we represent with capital H. Henry. This is the name of the scientist. So
yes, sir. Done, sir.
done. Okay. Okay. So now what we will do, we will calculate this M. We will calculate this M.
Okay.
For different construction, we will calculate this M. See this
Yes.
construction first. This is the construction. We can say this is a construction. See, here are two solenoids, coaxial solenoid. These are the coaxial solenoid. This is given in NCERT.
Yes, sir.
We want to find the coefficient of mutual induction, means we want to find M, capital M. Coefficient of mutual induction for a pair of two long solenoids of equal length placed one inside another. See this picture for 1 minute. Okay, see this picture for 1 minute and see all these what I have written here.
Yes, sir.
Okay. Okay, now I am explaining. So this is one yellow color solenoid. This is one yellow color solenoid, and
Yes, sir.
sorry, this is one white color solenoid first. This is bigger solenoid. Bigger solenoid, white color.
Yes, sir. White color.
Yeah. Smaller is why I'm saying length of both same. Length of both is same.
Yeah.
But radius, if you
But the
will
one is
talk
inside
about
of
the
the other.
radius,
Yeah.
yeah,
Radius is
radius
small.
of this white color solenoid is greater than the yellow color
It's bigger than
solenoid.
that of yellow.
Yeah.
Yes,
And
sir.
both of the solenoids are coaxial. Both of these solenoid are coaxial, means they have the same axis. They have same axis. Like here I have, this is shown. This is the axis. Both have the same axis.
Yes, sir.
Both have the same axis. And I have told you in a solenoid, I have told you in a solenoid what happens. Suppose this is your solenoid. Solenoid is basically a wire, and in this solenoid there is a current I, and this current is leaving like this. So in this solenoid, the magnetic field I have told you will be axial. Magnetic field will be like axial. So magnetic field will be axial. Okay.
Yes, sir.
Magnetic field will be like this. We can draw. So magnetic field I have told you will be axial. This will be the direction of the magnetic field. Is it or not? I have told you now.
Yes, sir. Yes.
For case of the solenoid, we take the axial magnetic field. For the case
Yes.
of the solenoid, we take the axial
Axial magnetic
magnetic
field.
field. Okay. So this we know. So here the direction of the magnetic field will be axial like this. The direction of the magnetic field will be like this.
Axial. Yeah.
Yeah, axial like this. And if you are taking this coil, if you are taking this coil, this is the coil, okay? This is one coil of the solenoid. This is one circular coil. So this circular coil, the area vector will also be in this direction. The circular coil, for this circular coil, the area vector will also be in this direction. Na?
Yes, sir.
Area vector. Area vector
Yes.
will also be in this direction.
Yes, sir.
And magnetic field vector is also be in this direction. So what is the
Yes.
angle between the area vector and the magnetic field vector? 0 degree. Okay. Area vector is perpendicular to the plane of the coil. So this is one coil of the solenoid. So perpendicular to the plane of the coil will be this direction.
Yes,
Okay.
sir.
Okay. So here that is why I have written magnetic field is in this direction, area vector is in this direction. So theta is equal to 0. And for the coil, this coil R1 for the white color, if I am saying a coil, so means this is one coil, this is two coil, this is third coil, fourth coil, fifth, sixth. Basically, whole thing is a solenoid. So for this white color solenoid or bigger solenoid, radius is R1.
Yes, sir.
Radius is R1 and length is L. N1 is the number of turn, or you can say number of coil. When you will give one turn to the wire, then it will become a coil. Okay. Here is one turn, here is one turn, then it will become a coil. So number of turn in solenoid per unit length for solenoid number 1. For the solenoid number 2, R2, L and N2. I have written all these things: N, small n, number of turns per unit length, capital N, total number of turns, or you can say total number of coils, total number of turns, or you can say total number of coils. And I have also written this is the magnetic field. This is the magnetic field due to a solenoid. Due to a solenoid, when there is a current in the solenoid.
Yes, sir.
So suppose I am giving I1 current to this white color solenoid. I1 current to this white color solenoid, and this current is changing with time. This current is changing with time.
Changing with time.
So yeah, changing with time. So now see, basically I1 is the current. Now see only this white color solenoid. See only this. What will be the magnetic field due to the white color solenoid? That is V1 is equal to mu naught
mu naught
N1
N1
N1 into I1.
I2
I1 because we are taking this one coil.
Yeah,
Coil
yeah,
number one.
yeah.
Coil number one is white. Coil number two is yellow. So this will be the magnetic field, and this magnetic field will be inside this white color solenoid or axial. This
Yes, sir.
this magnetic field will be inside of this white color solenoid and axial also, inside and axial. So this yellow color solenoid will be in the magnetic field of yellow color solenoid will be in the magnetic field of white color solenoid.
Yes, sir.
So this magnetic field V1 will be inside of solenoid inside of solenoid 1. Okay, magnetic field inside of solenoid 1.
Yes, sir.
If I will say that what will be the magnetic field inside the solenoid number 2, then what you will say? So
B2 is equal to
no, because I2 is not given. Actually, see na, this is your white color solenoid, so magnetic
yeah,
field line will be inside. So this yellow color solenoid will also inside.
inside. Yes, sir. It will be
So
same.
means same. Very good. Very good.
Yeah. So B1 equal to
B2
B2 is equal to mu naught
Yeah,
I11.
B2 will also be mu naught N1 into I1.
Yes, sir.
V2 is the magnetic field inside the solenoid.
Solenoid 2.
Yeah. Inside solenoid 2. Okay, now it become very simple. Now this I1 is changing.
Yes, sir.
I1 is changing means this V2 will change.
Yes, sir.
Means the magnetic field is changing. Okay. So now see, take one coil of this solenoid, yellow color solenoid. One coil of yellow color solenoid with this color. This coil I am taking. Okay. So for this coil, we will calculate the magnetic flux. Okay. So we can write magnetic flux through each coil of solenoid 2. So for solenoid 2, the magnetic flux through each coil is given by magnetic field
Yes, sir.
to area
Area.
into cos theta.
Cos theta angle. Yeah.
And I have told you theta is equal to 0.
0.
So
it will be BA.
So what is the magnetic field? What is the magnetic field? Mu naught
mu 0
N1
N1
I1.
and I1.
Mu 0 N1 into I1.
Yes, sir.
What is the area of the coil? We will take here area of the second solenoid coil. Second solenoid coil. Radius having the radius R2.
R2.
Yeah.
Pi
This
R2
will be
square.
yeah pi R2 square. Pi R2 square. Okay. So basically this is the magnetic flux linked with this coil 1. If we want to calculate the total magnetic flux through all the coils for solenoid number 2, then what we will do? Total flux will be multiplied by N2. N2 is the number of turns or number of coils in solenoid 2, and we will multiply this. Mu naught N1 I1 into pi R2 square. Mu naught N1 I1 into pi R2 square. And what is this? Phi is the total flux.
Yes, sir.
Total flux through solenoid 2. Total flux through solenoid
2.
and we know that N2 is equal to N2 by L. So from here we can calculate N2.
Yes, sir.
N2 is equal to N2 into L. So we will put this value here. So 5 will become N2 into L mu naught N1 I1 N1 I1 pi R2 square. And what is this? This is the flux in coil 2. This is the flux in coil 2. This is the flux in coil 2. And there is a relation flux in coil 2 is equal to M into current in coil 1. Suppose this is your equation number 1. This is your equation number 1 and this is your equation number 2. So you can write this equation, you can write this thing like this. Phi 2 can be written as
Sir. We have done this actually.
We have completed this.
Yeah, I just turned my pages on some mutual induction and this solenoid thing. So the final answer is M is equal to mu 0 N1 N2 L pi R2 square, right?
Pi R2 square L.
Yeah.
So till where I have completed?
So you have completed till M is equal to the final answer. M is equal to mu 0 N1 N2
means this derivation we have completed. Okay.
Yeah, it's completed.
Okay, no problem. So this is just left little bit, so we will complete it now. Okay.
Yeah. Because I turned the picture, so I think we are done this. So I turned.
Okay, no problem. So think this as we are revising.
Yeah.
Okay. So now I can write this as mu naught N1 N2 mu naught. This is mu naught. This is N1 N2 into L.
L
Into pi into R2 square into I1. So now compare this equation 1 with equation 2. So you will get the value of M as mu naught N1 N2 L pi R2 square.
Yes, sir.
This will be the coefficient of
yes, sir.
Basically in the last classes I have told you we will discuss from the self inductance. Self induction.
Yes. No, sir, I actually forgot due to exams.
Okay. Okay, no problem.
Okay, done. So now I can start self-induction.
Self-induction. Okay, just wait a minute.
So the self-induction is the last topic, right?
Self-induction is the last topic.
Yeah.
Just wait.
Yes, sir.
Self-induction. Sir, what is self-induction? Self-induction is a property of one coil.
Yeah.
Self-induction is a property of one coil. So basically, self-induction. Yeah. Self-induction. Self-induction. Basically, we have one coil and this coil will be connected with some battery. And when you will connect this coil with battery, the current will start flowing this coil. Okay, and here is one key, and initially here is one key. Here is one key, and now
Yes,
you
sir.
have closed this key. Suddenly the current will start increasing in this coil. Suddenly the current will start increasing in this coil. Okay, so when the current will start increasing means the magnetic field start increasing, and due to the increase in the magnetic field, magnetic flux will start increasing linked
Increasing,
with this
yes.
coil.
Yes, sir.
Due to the magnetic field, magnetic flux linked with the coil increase, and change in the magnetic flux will produce the induced EMF. So in this coil also there will be an induced EMF and there will be an induced current in the opposite direction. In the opposite direction. So basically when this current I in the coil will increase, basically when this current I in the coil will increase, this current I in the
Yes, sir.
coil will increase, there will be the induced current. There will be induced current.
Induced current.
There will be induced current in coil. That is I. Okay, so see one thing. When this current is increasing, when this current is increasing, there will be an induced current in the opposite direction of the given
Direction of
current.
the, yeah. Yeah, it will resist the,
According to the Lenz law. This will
yes,
be
sir.
according to the Lenz law.
Polarity of the induced EMF is always in the opposite direction of the,
Yeah. So if this current I is decreasing, current I is decreasing, then in this circuit, the current will be induced in the same direction.
yes, sir.
The current will induce in the
Same
same direction.
direction.
When I will decrease, so you can say current induced in coil in same direction of given current. Same direction of the given current.
Induced current.
Here current I is increasing. That is why
Yes,
this
sir.
current is in the opposite direction of the given
Direction.
current. So you can write here, this is the opposite direction of
Given current.
given current. So here you can write self-induction is a property. We can write here self-induction is a property of coil due to which it opposes any change of current through itself. Through itself. By inducing an EMF in itself. In itself. Okay.
Yes, sir.
So basically, if you will increase the current here, there will be increase in magnetic field and there will be increase in the magnetic flux. So we can say that the magnetic flux in the coil is directly proportional to the current.
Current, yes.
When we will remove this, we will get a coefficient of self inductance L, Li. What
Li.
is L? L
Inductance.
is the is known
Coefficient
as
of
the
inductor.
coefficient of self induction.
Inductance.
Inductance, you can say coefficient of self inductance. And what is phi? Phi is the flux linked with
Flux.
coil. Linked with
Yes.
coil. So now, according to the Faraday law, we can write E is equal to minus d phi by dt.
d phi by dt. So phi is equal to Li.
Yeah, E is equal to minus dy by dt, and phi is equal to Li. So EMF we will get E is equal to minus k L minus
Di
L
by
di
dt.
by dt. So this will be induced EMF due to self inductance.
Self induction. Yes.
And SI unit of L is Henry.
Henry.
SI unit of L is Henry. Okay, note down.
Yes, sir.
Oh, sorry. Harsh, are you getting?
Yes, sir.
Oh, fine. Harsh, are you available tomorrow? Because
I'm available, sir.
you are available now because already you have missed so many classes. So syllabus issue, na there will be syllabus issue. So
Yes.
I think I should take your class on tomorrow.
Yes, sir.
Yeah. Then only we will finish the syllabus on time because already due to the exams, you have missed the classes. Okay. So no problem. We will compensate, but we have to apply extra effort.
Yes, sir.
So at what time?
So same time you can keep.
Same time. Okay.
So done. So can you scroll down?
Sure. Okay. So basically, na, here one of the most important thing is Faraday's law of electromagnetic induction and Lenz's law. These
Yes,
you
sir.
are you can just analyze these two. We are using again and again, again and again,
Yes,
again and
sir.
again.
Done, sir.
Okay, now simple derivation we will see. Simple derivation. Simple.
Okay.
Self inductance of a circular coil we will see now. So
Self-internal circular coil.
yeah, self inductance of a circular coil. This type. Okay, see what is happening. First, you should know. First, you should know if a circular coil carrying a current I, if a
Yes.
circular coil carrying a current I having a number
Number.
of turns n, okay, and
Okay.
radius is r, then
R
magnetic field is given by
mu
mu
naught
naught
ni by
ni
2r.
to r. So this thing first keep in mind.
Yes, sir.
This will be used. So this is the circular coil here. This is a white
Yes.
color coil is a circular coil, and this is a circular coil having a current I, and there will be the magnetic field inside this coil.
Yes, sir.
There will be the magnetic field, and this magnetic field is inward. Why this magnetic field is inward direction? Because when you will apply the right hand thumb
Right
rule,
hand thumb rule.
curl your fingers along the sense of the current, and the thumb
Yeah.
will give you the direction of the magnetic field. So that
It's
is why
inwards.
this magnetic field is in inward direction. And okay, so we can say n is the number of turns for this coil, r is the radius for this coil. Okay, and this is the inward magnetic field. This thing clear na? Till
Yes,
here
sir.
clear?
Yes.
Okay. Area of the coil will be pi r square because
Pi r square.
this coil is circle.
So,
This
yes,
coil is
of course.
circular coil. So basically now I am telling you how the self inductance will be there in this coil. How the self inductance will be there. See what is happening. If I say this current is changing, if I say this current is changing with time. So what happens when what happens? This current will change means this magnetic field will change.
Will change.
Magnetic
Yes.
field will change means the magnetic flux linked with coil will change.
Will change.
Magnetic flux linked with coil will change means there will be the induced EMF
Induced
in this
EMF.
coil, and there will be the induced current also.
Yes, sir.
Okay. So basically we want to find the self inductance of a circular coil having n turns. Okay, self induction of a circular coil having n turns. Okay, so inward direction is represented like this, outward direction is represented like this. So now see, I want the total flux linked with this coil, this circular coil will be nba cos theta, and theta is equal to 0. Why theta is equal to 0? And what is theta? First of all, you should know what is theta. Theta is the angle between the area vector of this coil and the magnetic field vector. So see, the magnetic field vector is inward. Inward means perpendicular to the
Perpendicular.
plane of
Yes,
this
sir.
coil, and area vector of this coil will, I have told you many times that for a plane coil the area vector will always be perpendicular to that coil. So this coil is in this plane. So for this coil, area vector will also be in the downward direction. It can be in the upward direction, no, in the downward direction. It can be in the outward direction also, but we are taking in the inward direction. Okay, not
Yes, sir.
downward direction, sorry. So area vector of this coil will be in inward direction. Magnetic field is also in inward direction. That is why theta is equal to 0. Total flux linked with the coil is given by nba cos theta. Why I am taking n? Because n is are the
Number of
number of turns. So
turns.
nba cos theta is equal to 0.
0.
Now we know the magnetic field. What is the magnetic field? This will be the magnetic
Base
field,
mu naught ni by
and
2r.
we know the area of the coil. We know the area
Yes,
of
sir.
the coil
2
pi r
pi
square.
r square.
So we will put all the values here, and we will get
Okay.
this total flux. Total flux we will get this.
Yes, sir.
Okay, and I have told you in the beginning, phi is equal to li. I have told you na. Just check
Pi
your
is equal
notes.
to
Whether I have
yeah.
told you or not, phi is equal to li.
Just a minute.
Okay, yeah, check your notes. And this formula also I have told you, E is equal to minus L di by dt.
Yes.
Okay. So phi is equal to li na. When you will compare both the equations, so when you will compare na, so you will get this L. You will get this L, okay? Because this phi t and
Yes.
phi t will be cancel out. This current and this current will be cancel out. This L will be equal to mu naught n square pi r by 2. Mu naught n square pi r by 2.
Sir, I'll copy this down, sir.
Okay, just copy. This derivation is very, very easy, but
Yes, sir. Yes.
at the same time, you should know this formula. At the same time, you should know how to find the direction of the magnetic field due to a current carrying coil. You should know what is the formula of the magnetic flux, how to calculate the total flux. You should know what is the area of the circle. You should know the value of the cos 0. Then only you will get the answer. We have to be fast, okay, because our syllabus is already, we are lagging.
Yes, sir.
Why we are lagging? Because in other classes I am teaching, I have just finished that alternating current, and I am just I will start the electromagnetic wave. But okay, no problem, we will chase them, because there is you have missed the classes due to the examination. Okay, but the examination is equally important.
Yes.
We cannot leave the examination. So electromagnetic wave is very small chapter, but the concept
Yes,
is
sir.
very high. But when you will see na, that chapter conceptually, that chapter has changed the uh,
It is full of
electricity
theory,
and
right?
magnetism. Huh?
It is full of theory, right?
It is of theory.
Yeah. Like I studied that chapter and was full of theory.
Hmm. Light is an electromagnetic wave. Light is an electromagnetic wave.
Yes.
Hmm. Like here we are discussing that the changing magnetic field produce the electric field. There it will be proved that uh, by Maxwell that changing electric field also can produce the magnetic field.
Yes,
So
sir.
this will be this we will see there electromagnetic waves.
So we have scroll
And
down.
yeah, and alternating current chapter is very easy. Believe me,
Yeah.
very easy. I think it will take 1, 2, and 3, and I think 4 lecture it will take.
Done, sir.
Okay. Now we will see the self inductance of a solenoid. Simply we will use the formulas. Simply we will use the formulas, and simply we will apply the concept of again and
Yes,
again
sir.
the Faraday's concept. Okay, Faraday's concept of electromagnetic induction we will use. So see, this is a solenoid. This is a solenoid. I have told you, na, solenoid, and this solenoid have n number of turns. This
Yes, sir.
solenoid has n number
N number of
turns,
turns.
and this is one circular coil of the solenoid. This is one circular coil of the solenoid. I have told you this right here. I have told you. I think somewhere else I have told you. So here this is a solenoid, na. So this solenoid have this coil,
Yes, sir.
This solenoid have this coil. So area vector will of this solenoid will be in this direction. Magnetic field will be all in this direction. Then angle between area vector and magnetic field equal to
This
0.
will be 0.
No. Now no problem in this. Number
Yes,
n
sir.
small n number of turns per unit length. Capital
Yeah.
N number of total number of turns, or you can say total number of the coil.
Coils. Yes.
As this is a solenoid, so magnetic field produced by a solenoid is given by mu naught Ni.
Yes, sir.
Flux linked with the solenoid is given by Ba cos theta, and
BA
theta is
cos
equal to
theta.
0.
Yes.
And what is magnetic field? Mu naught Ni. And area of one coil. Area of one coil is given by pi r square. So this is the
Pi r
flux
square.
linked. Phi is the flux linked with this is phi.
Yes.
And when you will
Phi
solve
is
this, you
first
will
thing
get,
with coil 1.
yeah, this cos 0 is 1. Cos 0 is 1.
Yes.
So you will
Yes.
get mu naught Ni pi r square. Mu naught Ni pi r square. So what is phi? This is phi is the flux linked with the coil 1 of the solenoid. So with this one coil, the flux linked will be this. I am just
Yes.
taking up the speed because we already done this thing so many times.
Yes, sir. Yes.
Okay.
Yes.
Okay. Fine. Now, if I want to find the total flux through this solenoid, then I will multiply this value with n.
N.
Okay, very good. And what is n? N is equal
N
to
is
small
NM.
n into L.
L,
So
yes.
I have put this value here. And what is phi t? Phi t is representing the total flux. Phi t is representing the total flux.
Total flux. So final will be mu naught
Okay.
n
So
square.
this
A
will
r
become
square.
nl mu naught ni pi
Yeah.
r square. So you can write this in the form of this mu naught n square pi r square L
L
and
by
I.
into
And
I.
I have told you this formula also, total flux
Yes.
in the coil is given by
Li.
L into I.
Li.
And you will compare this equation.
Compare 1 and 2.
Do you know how to compare the equation 2 and 1?
Yeah, LHS and RHS will be equal.
Yeah,
right?
yeah, very good. Well done. Then you will get this answer. Then you will get this answer. This is the self-inductance of the solenoid. Self-inductance of the solenoid. See this
Yes.
here we should know, first we should know this formula. See what are the requirement to drive this. First we should know what is the direction of the area vector of this coil, of the solenoid. We should know the magnetic field should be along the axial direction.
Yes.
We should know what is the formula of the magnetic field with the solenoid having the current I. We should know the formula of the magnetic flux. If you know these things, and then if this thing also you should know for comparing, then you can easily find this value. Okay, write down first.
Yes, sir. Yes, sir. Second scroll. Second scroll down. Done, sir.
Inductor, we will discuss inductor now. Basically, inductor
Okay.
is simply this. This is inductor.
Let's say current pass.
Inductor is a coil like this. Whenever the current changes in inductor, simply remember EMF will be induced. And why this? Why when there is a change in the current in the inductor, why EMF is inducing in the inductor? Why? What is the reason?
Flux changes.
Yeah, good. Because see, this is the current in the inductor. If this current is changing, then due to this current, magnetic field is changing. If magnetic field is changing, magnetic flux linked with the inductor changing. Magnetic flux
Yes,
is
sir.
linked with the inductor changing. According to the Faraday's law, changing magnetic flux induces the EMF. So there will be induced
Yes.
EMF, and that induced EMF is given by E is equal to minus L di by dt.
Li by dt. Di by dt.
So basically, inductor consists of a number of turns of an insulated wire. It opposes the change in the current. Why it
Yes.
opposes the change in the current? I have told you.
Yes.
Now this is the inductor. When you supply the current to the inductor, what happens? Suddenly you supply the current to the inductor. What happens due to the change in the magnetic flux? There will be the induced EMF in the opposite
Yes.
direction.
Yes, sir.
There will be the induced
Induced
EMF,
EMF in the
or you
opposite.
can say there will be the opposite induced current. Means there is a current which opposes the increase of this
Resistance.
current.
Yeah.
That opposes the increase
Yes.
this current. So see here, we will discuss this. Magnetic energy is stored in the inductor. So suppose this is your inductor. This is your
Yes, sir.
inductor, and this inductor is connected with battery. And this is the
Battery.
key. This is the key.
Key is open.
This is his key. This time the key is open. There is no current. There is no current.
Yes.
At t is equal
No
to
current.
0 means initially current in the inductor is 0. EMF induced will be 0 because there is
Zero.
no current, so no
Induced
induced
EMF
EMF.
is also zero.
After some time,
No current.
at t is equal to t, after some time, you have closed this key. So there will be
Yes, sir.
there will be a current in the inductor, and there will be the induced current in the opposite
Yes.
direction. I have told you. And what will be the
Yes.
induced EMF? L di by dt minus L di by dt. I have told you. I have told you, na, L di by
Yes.
dt. Okay, very good.
Yes.
Fine. And this battery have the EMF E. This battery have the EMF
EMF.
E, and this E is equal to minus E. Why this E is equal to minus E? Because this induced EMF here will oppose the increase in current. When you just closes this key, current starts increasing. Current starts increasing means magnetic field starts increasing in this coil. Magnetic field start increasing means magnetic flux linked with coil increasing, means there will be an induced EMF, and due to that induced EMF there will be an induced current in the opposite direction of this increasing current. So basically you have to provide some extra energy or extra power from your battery. Okay, you have to provide
Yes.
that extra power to overcome that resistance or to overcome that induced current. Okay, so that is why this E is
Yes.
equal to minus E. Okay, E is equal to minus E, so you can write this E is equal to minus of minus LDI by dt. Basically E you will get LDI by dt.
LDI by dt.
Okay,
Just change the sign.
yeah,
Positive.
change the sign because this is here is minus E.
Yeah, minus.
Now this current is increasing when you have opened, when you have closes the key. So current, initially the current is 0, finally the current becomes something I. So the current is changing from 0
Yes.
to I. For that changing current 0 to I,
Yeah, it is increasing.
the energy is spent by the battery stored in the inductor as the magnetic energy. So that energy we want to calculate. That
Yes.
energy we want to calculate. Now see what I am going to do. Basically this is our battery or cell, you can say. So work done by the cell to change di current in the coil in time dt. So in time dt, in small time, we will first calculate small change in the current in the inductor, then we will integrate, then
Yes.
we will get total work done to change the current from 0 to I.
Yes.
Okay, so that small, basically this thing you should know. Power is given by work done divided by time taken.
dWdt. Yeah.
P is equal to dw by dt.
dt.
Okay, and power is also given by EMF into current.
Yeah.
Yeah, so dw is equal to P into dt. From this
Yes.
formula, dw is
Yes.
equal to
P into
dw is
dt.
equal to P into dt. So dw is equal to P into dt. So dw is the small work done in changing the small current di. So what is P? Power of this circuit, EMF into current, EI into dt. Now integrate this equation. And put this value of E. What we have this value of E. E is equal to LDI by dt. So we will put this value here. So this is LDI by dt. So dt and dt will be cancel out. So we will have LIDI. We will have LIDI. This we will have. This term
Yes,
we will
sir.
have. Now we will integrate this. Okay, we will integrate this and we will
Yes.
integrate this. Here the limit of integration will be 0 to I naught. I naught is the maximum current, because in a circuit the current is increasing from 0 to some I naught value. Okay, so
Yes.
0 to I naught value, you will integrate this. So integration, I think you should know. If you are integrating I into di from 0 to I naught, then the answer will be I square by 2.
I square by 2.
You will apply the limit 0 to I naught, then you will get I naught square by 2. You will get this
Yes.
value. So basically this value you will get here. This is L into I. This is L, and integration
Yeah.
of this I.
Yeah.
I naught
I
square
square
by 2. So this will become half L I naught square.
I naught
So
square minus 0.
yeah, this is I naught square minus 0 square, because this is
Yes.
upper limit, this is lower limit.
Lower limit, yes.
But so work done to change the current in the inductor from 0 to maximum value will be half L I naught square. I naught is the maximum current, and work done by the, and this work done is stored in the inductor in the form of the magnetic energy. So work done by the cell, again the self induction will get stored in the form of the magnetic energy, that is given by half L into I square, or you can say I naught square.
Yes, sir.
So there is one question on it. There is one question. This question. See this question. They are saying an inductor have the inductance of 10 Henry.
Yes.
Means L equal to 10 Henry given.
10 Henry.
Connected to a variable supply of 10 ampere, means current
is equal to 10.
Maximum current is given as 10 ampere.
Yeah,
This will be the maximum. Rate of change of current is 10 ampere per second. Rate of change of current means di by dt is given.
Yeah.
Rate of change of current di by dt is given as 10 ampere per second is given. And they are asking number 1, induced EMF. What is the induced EMF in the inductor?
L di by dt.
Very good. What is L? Minus 10. So what is di by dt? This is become 100 volts.
Minus 100.
Very fast. Okay, so E is equal to minus L di by dt. This is
Yeah.
See, this is L na, so L is
Yes.
110, L is
Yeah.
10, and di by dt is 10. Simply
Yeah.
multiply minus
Yes.
10 and 10. Now energy stored in the inductor.
Half
Huh?
L I naught square, right?
Very easy. This is very easy. Such a easy question. So
Yes, direct
energy
question.
stored in the inductor is half
Half L
L
I naught
I
square.
square. I naught square
Yeah.
you can write. So
Yes.
what is half? Half is half. L is
Half
10.
L is 10.
I naught is 10 square.
10
So this will
into
become
square.
500 joule.
Yes.
So unit of energy is joule.
Yes, sir.
Unit of energy is joule.
Joule.
Now there is one topic left, that is energy density. Have we calculated the energy density somewhere else also?
Yes, sir. In the previous chapter, J is equal to I by right.
No. We have
There is a
calculated the energy density for the capacitor. Energy density.
oh
So this is your last topic, energy
yeah.
density. Okay.
It's
So
same.
okay, note down this.
Yes.
Energy density is your last topic. Then after that, tomorrow we will have a same class at the same time, and we will start the AC, alternating current.
Yes, sir.
Okay. So please don't miss the class.
No, sir. I will.
Hmm. Harsh, can I speak in Hindi little bit?
Yes, sir. You can.
आई एम सेइंग दैट ना, मुश्किल हो जाता है कभी कभी के, जैसे कुछ चीज मैं बता रहा हूँ और पीछे की चीज नहीं पता है। जैसे कि
जी
मैं बता रहा हूँ, जैसे कि मैं किसी को बता रहा हूँ कि फोर्स इज इक्वल टू मास इंटू
Mass into
एक्सेलरेशन,
acceleration.
बट उस बंदे को यही नहीं पता कि एक्सेलरेशन क्या होता है, तो वो ये नहीं समझ पाएगा।
जी.
तो ये इम्पोर्टेंट होता है कि हमें पीछे की चीजें, एटलीस्ट आई एम नॉट सेइंग यू शुड बी वेरी वेरी गुड इन दैट, इट इज बेसिक थिंग यू शुड नो। सो
Yes.
दिस थिंग विल बी फॉलोड इन फिजिक्स, अदरवाइज यू कैन, कोई भी टीचर पढ़ाएगा, जैसे कोई भी टीचर पढ़ाता है, तो एट द सेम टाइम ना, ऐसा होता है कि अगर थोड़ा सा बच्चे को, अगर थोड़ा सा भी पीछे की नॉलेज है, जैसे कि अगर मैं कभी पूछूं कि व्हाट इज द चार्ज ऑन द कैपेसिटर, व्हाट इज द रिलेशन बिटवीन द पोटेंशियल डिफरेंस एंड चार्ज एंड द कैपेसिटर, सो अगर बेसिक थिंग्स पता है ना, तो आगे की चीजें बहुत ज्यादा क्लियर हो जाती है।
जी.
ये रहता है। हाँ, जैसे ऐसा नहीं है कि अगर जैसे नहीं आता है तो वो नहीं कर पाएगा, बट उसमें थोड़ी सी प्रॉब्लम होगी, एक्स्ट्रा एफर्ट देने पड़ेंगे, देन इट्स ऑल फाइन। So basically na inductor, what is the inductor? Inductor opposes the change in the current.
Change of the
If in the inductor the current is decreasing, if in a inductor suppose the current is decreasing, then that inductor induces a current to support that current. Means
yes.
induces the current in the same direction of the given current that is
Yes.
decreasing. Okay,
Yes, sir.
and this is based on the Lenz law. This is based on the Lenz law.
Lens law. Second scroll down.
Yeah.
So you can scroll down.
Okay. Harsh, can you send me your physics paper?
You can scroll down. Yes, sir. I'll send you, sir. After the
Okay.
class, I'll send you.
Okay.
So you can scroll down.
Yeah.
Done, sir.
Done, completed?
Yes, sir.
Okay, Harsh, so we will meet tomorrow at the same time. Okay.
Okay, sir. Okay, sir.
Okay, fine.
Thank you, sir. Bye, sir.